Hey guys, so this video and the others like it are meant to replace me today, so hopefully you can learn from them just like you would if I was still in the classroom. Now, this is the first video I'm making, but it's actually going to be the third in the series. Videos 1 and 2 cover old information. This one will be over the genetic code, which if you were in class on Friday is right where we left off. In your guided notes, it's going to cover from question 12 to 18. And then the rest of it, the very ending, will be video 4, which hopefully breaks these down into kind of like manageable chunks, all right? So that's the plan. Let's go ahead and get started. Now, just to recap and remind you where we left off on Friday. On Friday, we did transcription. We took DNA, turned it into RNA. Used a funky enzyme called RNA polymerase to do that. Today, the focus is going to be on translation. So we're going to take that RNA we made and turn it into protein, this step here. To do that, first we need to talk about genetic code and how genetic language works. So this video is kind of like more of an overview / background. The next video will be more about the process. Okay? Now, the first thing you need to know is that the genetic code is made up of words. These words are called codons, and unlike English, where words can be all different lengths from short, at, of, is, to long, triskaidekaphobia, anti-disestablishmentarianism, the words in the genetic language are always 3 letters long. No exceptions. So a codon is always exactly 3 bases. A-U-G, 1, 2, 3, that's one word, one codon. AAC is also one word, one codon. And then UCU here, you got it, one word, okay? So just the words in the genetic code are always 3 letters long. It's like if our entire vocabulary was the cat ran. Every word was 3 letters. Okay, when we translate, we're going to turn those codons into amino acids because proteins are made of amino acids. So if we're making a protein, we're going to do it 1 amino acid at a time. Guys, this is number, where are we? This is number 14 in your notes. It's kind of important. 1 codon equals 1 amino acid. So for every 3 letters of nucleotide, we'll get 1 amino acid. UGG, 1 codon, you're getting it, 1 amino acid. UCA is 1 codon. It gives SER, 1 amino acid. All right? So this, to get from RNA to protein, that's the goal of today. If we can do that, we've done a good job. Now, to help us do that, we're going to use what's called a genetic code. Genetic code, think of it as the RNA to protein dictionary. Same as if I wanted to translate from Russian to French. I'd go out, I'd buy a Russian to French dictionary. I can look up one and it tells me, oh, that means this other word. So this is going to take us from the RNA to the protein. For example, just to make up a codon, if our codon was ACA, all right? Notice how this thing is labeled. First letter, second letter, third letter, which you'll actually probably never use. Okay, first letter, second letter matter. First letter is A. Let's see, first letter A, that means I'm using this row. Okay, so it's gonna, my answer is somewhere here. And you can start looking, you'll probably find it, but if you want to be fast, second letter is C. Second letter, C. I'll be using this column. So my answer is in this box. Remember how I said most of the time the third letter doesn't matter? Notice anything beginning with AC, including ACA right here, always gives the same amino acid, THR. And if you look over here on this side, THR stands for threonine. So that is what I would write. I would just write the 3-letter abbreviation, THR. Sometimes I'm going to ask you to use the first letter abbreviation. Okay, so that's just this letter here in parentheses. Sometimes we'll use that, okay? So it's not a hard thing to use, really. It's kind of like code breaking. Okay, there are 3 codons that are more important than others. The first is the start codon. Start codon is down here, okay? And it is AUG, stands for the amino acid methionine. Methionine is abbreviated MET or M. Okay, so start codon is the first codon in all amino acids. Excuse me, the first codon in all genes, which means all proteins start with the amino acid methionine. Okay. The other 3 important codons are the start codon. Now they're all labeled up here in the corner. UAA, UAG, UGA. Think of them as the punctuation. You can have a period, you can have an exclamation point, you can have a question mark, but all of them mean this is where the protein ends. Okay? So 1 starting, 3 ending, in between everything else. Now, what we're going to do on a test and on your homework and on a test review and in our activities this week is I'm going to give you a piece of RNA, ask you to translate it into protein. This is question 17 in your notes, by the way. Okay? And by the way, go up and compare it to question 11. That RNA should look pretty familiar. First thing we want to do is we want to divide it up into codons. So that's 1, 2, 3, 5 codons. All right? 5 3-letter words. And then we're just going to take each codon one at a time. So first letter is A. First letter A. Second letter is U. Second letter U. That's going to put me right here in this box. And if it isn't, our old friend, AUGMET. Okay? 1-letter abbreviation, M. So that's basic process. What I want you to do now, pause the video and try to do this on your own. See how good you are right now without much practice. Let's give you an idea of how easy this week's going to be or how hard this week's going to be, or how much you need me in tutorials. So pause it, try, never hurts to try, and then come back and let's see how well you did, okay? So, bye. Hello. Missed you very, very much. So, let's see. Hopefully, first letter C, second letter G, that's over here. Woof. So we're all the way at this end, and sure enough, CGA is right there. ARG, the pirate amino acid. Not really, it's arginine over here. Notice arginine does not get abbreviated A. That's alanine. Can't abbreviate all of these A, so arginine gets an R. Okay? Next one is GGU. G again, right over here. Oh, forgot about that. There's a typo. That is not supposed to be a D, that's supposed to be a U. Hopefully that didn't throw y'all up, guys. I'll need to fix that. I have homework. Okay, anyway, on this, you know there's no T, so T should have been a U. Still works the same. It's GLY, which is glycine. GLY over here. It's this 1-letter abbreviation, G. And then finally, UCG. UCG. UC here. So right here, UCG, serine, S-E-R. That's pretty straightforward. That's an S. UGA, U again, G, this box. Oh, look at that. UGA is our familiar friend. Stop. And that's what we do. We stop. So, met, arg, glycer, or MRGS. Hopefully that's doable. Hopefully that's what you got. I'm sure it is. I teach smart students. So, oh yeah, one last fact about today. This genetic code, this dictionary, is universal, meaning all life uses the same dictionary, which means if I move a gene from one organism to another, they'll still make the same protein. Now, if you notice, we got some funky looking animals here. What we've done is we've taken GFP, green fluorescent protein, from jellyfish. And we all know jellyfish glow in the dark. We take that glow-in-the-dark protein, GFP, out of jellyfish, and we've put it into the DNA of other organisms. So the rabbit makes green fluorescent protein and glows in the dark. Meet Alba, the bunny. The mouse makes green fluorescent protein and glows in the dark. The glowfish, you get the idea. Guys, you can buy these at a grocery store. Not a grocery store. You can buy them at a pet store and get yourself some fish that glow in the dark because they have jellyfish genes. Now this goat over here, it's kind of different. We took the gene for spider silk out of spiders and put it in the goat. You're like, what the heck? It makes the silk in its milk. We then harvest that silk by dehydrating the milk, and we can spin it into thread. And guys, that thread makes clothing that is stronger than Kevlar. It's more bulletproof. And this goat right here is going to save lives someday. We can also do it with human genes. For example, we take a human gene like insulin. We put it into bacteria. Okay. The bacteria then make human proteins. And if anybody in your life is diabetic and has to do insulin injections, it's human insulin, but I guarantee you it came from bacteria. So this is all called genetic engineering or transgenic organisms. It's a pretty cool field. It's highly bizarre. And if you're looking for a job someday, talk to me because I used to do some of this. All right? So that's a good stopping point. We're going to pause here. And this I'll pick up in the next video. So tag along, head to video 4. I'll see you there.